Does he still play? Wow, see, that's a little sad. He should.
He brought him out one time, but it didn't make any sense to me because he was like trying to explain it quickly.
Oh yeah, no, it's not a game you learn quickly. And from what I found, it's not a game that most females will tolerate learning.
Yeah.
But that might be the company that they would typically have to keep while playing, too. Yep. All right. Let's talk. There are tables that list data for various particles of matter that physicists have discovered. Often, such tables list the masses of those particles in units of energy, such as MeV, million electron volts, mega electron volts, rather than in kilograms. The Higgs boson was found to be somewhere on the order of 120 giga electron volts in mass, for example. Why is this possible? How can we do this? E equals mc squared, right. That mass energy equivalence means that we can say that it's an equivalent amount of energy to this mass. It is still a little weird, but it also allows you to take into account energy, the kinetic energy that it would have during movement. But it is still strange. It's a little easier in that you've got a big number rather than a really, really tiny number. Because if we were talking about the mass of the particles, like an electron is somewhere on the order of 9 times 10 to the negative 27 kilograms, that's a cumbersome number. So saying it in a whole number is a little bit easier than to do it that way. Why is it easier to accelerate an electron to a speed that is close to the speed of light compared to accelerating a proton to the same speed? Yeah, electron's a lot lighter, less mass than the proton. Nothing, that's an old school type of question. Finally, light travels in water at a speed of 2.26 times 10 to the 8 meters per second. It is possible, in principle, for a particle that has mass to travel through water at a faster speed than this. So faster than light. In what sense, then, does the speed of light represent the ultimate speed attainable by objects that have mass? Yeah, Elsa.
Light is the fastest in vacuum, and water it gets way slower.
Right.
So that's why we could try to get that.
Right. It would still be very, very difficult, but that is exactly right. We can't exceed the speed of light in a vacuum. But this isn't a vacuum. When you have water, like a surface of a water, if you've got a pencil sticking into it, it looks like it bends as it's going down. That's because in water here, light actually travels quite a bit slower, about 1/3 slower than in air. And whenever a wave goes over an area that it travels slower, it actually bends. And so that's what's happening here. We studied that in the other second semester of physics, how light is bending and things. But that is exactly why. Okay. If we get time, I'll come around and check with anyone who's got the second homework done. But we've got some nice stuff here today to talk about too. So I want to get back in that. Because remember yesterday we had started talking about the strange phenomenon is if we have a flash of light that occurs in the center of a very quickly moving box or train car here, and we have at the back of the train and the front of the train clocks that start when that flash reaches them. A person on the train would say that they'd start at the same time because the flash would travel equal distances to get to them. However, the clock B, to an outside observer, clock B is actually approaching the point in space where that flash was emitted, which means that it should be going towards the light, making that time shorter, while clock F in the front is actually going away from that point in space, meaning that it's sort of fleeing from light. Light only travels at C no matter who is observing it. So if the whole box is moving that way, that means the back clock starts a lot sooner than the front clock. And we would have some delay in the clocks as observed from the outside. And we figured out, hey, here's my pencil. I'll have to apologize to David if he gets out of the hospital.
What? We'll miss him anyway.
I've said too much. No, I was just asking him. I talked to him in here earlier this morning, and I said, did you walk off with my pencil? Because I can't find it anywhere. But if you see him, you can tell him that I was really angry, and I'm sure that he did it, and that I will be looking for him later. Okay, so yesterday we said that the difference in time, we derived all of this, and we said the difference in time that an outside observer would see would depend on the speed of the clock, of the train. And that this amount of time that we were measuring outside would be our delta t. And we said that it was the length of the train times its velocity over the speed of light squared, not an e, times our normal radical. And furthermore, because of time dilation then, we would have another weirdness because this is the time that we would mark on the outside, but the time that would actually be going on the inside between those two events, between when we saw the light start the back clock and when we saw the light hit the front clock, would also be a different time. That would be the delta t naught, which is this, delta t, times our radical. And if we multiply these two together, we get that that should be L naught V over C squared. So a couple of weird results, not entirely intelligible and understandable right now, but we are going to keep working with them. Okay, so we're going to use this in the next part. And here I have a bit of a description to set up the last part. Look though, not much math on this page. So, and we get to the result pretty quickly. Although what I'm not showing you is that there's another page. Deep breaths. Okay. All right. So, consider a fast-moving train in which a ball is thrown at high speed from one end to the other. Clocks at either end, synchronized to an observer on the train, time the flight. What is the ball's speed relative to a so-called still observer, an outside observer from the train? We're going to use some of these ideas. First, we're going to make some assumptions. First off, this L naught, that's the length of the train. So we're throwing it from one end to the other. That's also the distance the ball travels, according to someone on the train. T1 is the time on the back clock. T2 is the time on the front clock as those events start. So remember that these are timing the flight. So to a person on board the train, they'll read the same tick every time, and they're what's timing it. Yes, Matthew?
Where is this?
It isn't.
Should we write it down?
No. This as well, this is a really long one. I want you to do your best to first stay awake, second follow what's going on, and at least the arguments of how we're getting there. The math, I like to show that to you so you can see where it's coming from, even though I'm not going to test you on it.
I already failed the first part.
You talking in your sleep?
No, I already dozed off like towards the beginning. I'm done here. I don't know where we are anymore.
And so, what we call delta t in this event, or in this frame of reference, is going to be how much time the clocks say elapses according to a person on the train. So according to the front of the train. Okay? So, here's where we go from there. If we throw a ball, we would be able to measure the ball's speed on the train by saying how far did it go and dividing by how long it took as far as we know. So we're going to call that the velocity between the ball and the train. So if you were on the train, this is a velocity you'd measure. It would be the length of the train, L0, divided by the difference in the times of the clocks that are going along with us. Just a normal timing thing. Okay. Now I want to figure out what is the ball's speed relative to that person on the platform. And where we're going with this is that question of, if you are already moving at 0.8 c and you shoot something out of your ship at 0.7 c relative to you, how fast is it really going compared to someone else? Because it can't go 1.5 c. So that's where we're going with this. So we want to find VTP, the velocity between the train and the platform. That's pretty easy to measure. We're going to use an L. L is the length of the train that someone on the platform would measure. We already know what that would be. It would be the rest length of the train times our big radical here. The speed that the train is moving relative to us on the platform divided by c squared. Now, this next bit gets a little hairy. I know. We're going to say that T1, which the person on the train says is the time on the back clock, we're going to adjust that. That T1 prime is going to be what we on the outside see. This is where we're bringing in the stuff from yesterday and saying, how can we get these different times to peacefully coincide? That's going to be whatever we measure on the train minus that weird thing that we just reiterated from yesterday, minus the change in time, the difference in time. This was our delta T naught from our previous one. So what the time dilation factor would be. This is the time on the back clock as the ball passes that back clock, observed from outside. We're actually going to say the time on the front clock, we're going to agree with that, because we have to have one event in common. But that means that the other event is going to be at a different time. So if we start at or end at the same time, the other one has to be funky. Okay, and we are going to say then that if we watch these two, we're both observers are going to have different times. Here's how we can describe it. The proper time, the delta T naught, this would be in the train, measured by someone outside the train, would be the difference between these two. And I'm going to keep going with this, which is our same as saying that the time on the second clock minus what we've got right up here. Okay, and what this is right here is the time that a person on the train would say. And that's just simplified a little bit. All right. Now, the time elapsed in flight as measured by a clock on the platform. So now you're looking at your own watch and you say, okay, we just saw how long that would be on the train. How long would it be for you? That's we're going to call delta T prime. And it's related just by our old friend here. Here's what we're going to do instead. Long story short, we're going to skip ahead. Crickets chirping. And putting this all together, what we're going to say is we will come up with, if we follow all of this wonderful math through, which you really should take a look at sometime, we can describe that speed. we're going to describe the speed between the ball and the platform. So this is, you're outside the train, looking into the train, trying to measure the end speed of that ball that's being thrown. It's going to be a combination of things. The speed between the ball and the train, plus the speed between the train and the platform. This would just be what it is normally, right? If you are in the back of a truck throwing something, you're just going to add the two velocities, whatever your truck's going plus whatever your ball is thrown at. But now, here's where the relativistic part comes in. 1 plus the product of these two over c squared, the speed of light squared. This is a big one. So write this in your notes. This is relativistic addition of velocities. But I will spare you the rest of the wonderful, wonderful derivation. Even though you're missing it.
That kind of stuff.
What's that?
At what point in like college physics do you learn derivation, that kind of crap?
You'll start getting derivations if you're in like the engineering route fairly soon.
Oh, thank God not.
If you are going into if you're going into like a chemistry, you'll probably see a little bit of this.
Okay.
If you're going into a biology, you'll probably skip it. You'll take physics at a very similar level to what you've gotten here in this class. And it will be quite easy.
Can I go with that?
Yeah. If you can survive this class and take something out of it, you will do great in that level of physics.
Right.
If you're an engineer, there's still more to learn. Engineer or physics or physical science. There's another level to add on.
That's not a problem anymore.
Good stuff. Well, that's when you start adding calculus into it and saying not everything is quite as well behaved as we decide here. It's good stuff.
See, that's what everybody tells me.
Well, and actually the sad part is, I don't know that, I'm trying to think back. I'm not even sure how much more of this we did in college. This is sort of the lowest level that you can still do some stuff with relativity in. You could discuss what happens, but you wouldn't know at all why, or be able to do anything with it at a lower level. Whereas with a lot of the stuff we did last semester, there's a lower level. We got it. A lot of you got it in 9th grade. Some of you skipped that, and that's cool. But there are lots of different levels. There's no level below this. But let's see how we can use it. So previously, if we add velocities, let's say that Kayla foolishly stands in the back of a pickup truck. Don't ever stand in the back of a moving pickup truck. Okay? And throws a basketball in the same direction as a pickup's motion. If the pickup is moving at 22 meters per second relative to Zach on the side of the road, and I forgot to update everything. Kayla throws the ball at 27 meters per second. What would Zach measure for the speed of the ball? We don't have to complicate this one. It's pretty low speed. The truck's moving at 22 meters per second. The ball relative to Kayla in the truck is moving at 27 meters per second. So what total velocity would Zach see? 49, right. He'd see 49 meters per second. When we're at low speeds again, we don't have to take that relativistic part into account. Now, a spaceship, though, travels at 0.9 c, and it turns on its headlights. If you are an outside observer, how fast would you measure the photons from the headlight to be going? C. Everybody agrees on that. No problem there. It's weird because everyone would see it going C, even the person going 0.9 c. But everyone measures that as C. But now, is where it gets hairy. A spaceship travels at 0.75 c towards Earth and launches a torpedo at the planet. This will likely doom us all. If the torpedo's velocity relative to the ship is 0.85 c, how fast would an Earth observer see it approaching? Now, when we're starting to talk relativistic speeds, is where we have to do this. Because if we're talking that this would be the combination of the two speeds. If the speed of the truck is 22 meters per second and the speed of the ball relative to that is 27 meters per second, those two times each other are way smaller than c. This turns into 0 effectively. So we just have the sum of the velocities divided by 1. That's what we'd get with our first example up here. That's not the case anymore when we're talking at relativistic speed. So let's figure out how to use this in an example here. We are going, I want to redo these letters a little bit for a really general sense. And we're going to use 3 different letters, but we'll just use like A, B, C, because B and T only made sense in the train thing. Let's say that we have got 2 things moving relative to each other, A and C. This could be our ship and Earth. What we need to do, figure out the whole thing, the relative, is we need to know what is the speed between the BC. I know. What is the difference or what is the speed between the ship, A, and Earth? What is the speed between the ship and its torpedo? And then we combine those 2 things down here. So we're looking at, we want to find the difference between A or B and C. Yes?
So when you're looking at a problem, how do you designate which one's A, B, and C?
Good question. We'd have to look at what we know about this. And it's always a good idea to draw this out because direction here can make a difference. So let's draw that out. Here is our alien vessel. It's pointier than usual. Here is Earth. Here is its torpedo. Yes, it is a large torpedo, which is very menacing to Earth. That would be frightening. Yeah, and it's pronounced America. Well, but that might also that might scratch their paint job. They're just trying to, maybe they're just trying to get Earth out of the way to build some sort of intergalactic highway. Okay.
That's original.
Came up with that just now.
I'm sure you did.
So what this question that we're trying to do is figure out the speed between the torpedo and Earth. And we also have a ship in the way. So we want to find out what is VTE. That's going to depend on the other 2 in order to get it. So we're trying to find a combination of this speed with relation to Earth and the speed relative to each other. So between the 2, we'd have a VST, a V between the ship and the torpedo. Between the ship and Earth, we also know. That's not loose. Then the train? Really?
Huh? No, because you know two different lengths and you just solve
Right.
for the other one.
We solve for the other one. So since this certainly is in that direction, this one's in this direction, this one's in that direction, we don't really have too much to worry about. We're trying to find the product of this one and that one, which gives us the third. So up here, I would write, when I'm solving this now, I'm going to write this, here's my combined velocity. It doesn't matter which order I put these other two in, but it tells me which ones I need to solve for. So that final velocity will be velocity between the ship and the torpedo, which is 0.85 c, plus the speed or velocity between the ship and the Earth was 0.75 c, over 1 plus the product of those. Over the square of the speed of light, and the c's, of course, cancel as usual. Oh, that's what I did. I got 1.3 c. I think I did something wrong. I did. What'd you get?
0.977 c.
So are we saying the Earth is moving in that direction as well?
We aren't saying what direction, compared to what?
Because VSE, it's the velocity between the
So we are kind of saying that the Earth is still. We can't really do that. But because everything is moving. But what we can say is that the Earth and the ship are approaching each other. The ship and the torpedo are going away, but the torpedo and Earth are approaching each other. But we can't say that Earth is really still at all.
So,
One thing you can always do is sort of make a guess ahead of time and say, all right, these two things are both going towards the Earth, one at 0.75 c, one at 0.85 c. The combined speed should be bigger than either of them, and less than c. You'll work some examples that will make you think about direction a little more. Yes?
If you were on the ship, wouldn't you experience the torpedo and stop moving because it's not going as fast as...
No. So what the description up there means is that when you launch the torpedo from the ship, it looks like it's pulling away from you at 0.85 c. So that's what that measurement means.
do you feel any opposite force in the opposite direction?
I imagine you would a little bit. Maybe your ship engines are big enough to accommodate or something like that, but you bet. Yep.
So, ST means from the ship, the torpedo was doing something?
Comparing the ship to the torpedo.
So, VSE is from the ship, the Earth is
Right.
moving away?
No, they're moving together. This means that the velocity of the ship compared to the Earth is in that direction, towards the Earth.
So it's just basically the displacement once you find a little piece. You know the whole thing, and then the little piece you just have to find it.
Yep. When you draw this one out, I think it makes it easier. Tom's happy. That's the first one. First time this semester. Let's do another example. I know I'm pushing my luck here. We already answered this one, I think. Oh, Nope. We're on to the next page. I don't even have this one. Let's see what I got. Okay, so things to keep in mind when we're talking about these relativistic speeds. Light speed travel is not possible for anything with mass. We kind of saw that yesterday with our energy equation, because as things go faster and faster, what happens to their mass?
Heavier and heavier.
It increases. Well, if the mass increases, what happens to the energy you have to put into it to get it to go faster? It increases. It's one of those asymptotes that we looked at the other day. It goes to infinity. It's not a dirty word. It's not a dirty word. Asymptote. So, what does he say?
Asymptote.
Asymptote. Maybe the lingo has changed since he was in college. I don't know. We cannot just add them, so keep that in mind, because what that would lead to is breaking this first rule. If we added the 0.75 and 0.85, clearly it's more than C, and we can't have that. Okay, so let's consider another fast-moving train car, back on the train, with a ball thrown from one end to the other. This is just saying the three things that we're going to have to look at, three different types of speed, which we kind of hit at already. The velocity between the train to an observer. So that's the outside. In our case, that was from the Earth to the torpedo is what we're kind of looking at, the thrown ball. Or, sorry, the ship to the Earth. We'd have to look at the velocity of the ball relative to the train. So that's like between the two moving things, between the ship and the torpedo. Here. And, oops, I keep doing that. And look at the ball as obscene from an observer, which would be our final torpedo to the Earth. Okay. We already did that. We already did that. I think I didn't intend us to do that whole thing here. I think this was wait a minute, that doesn't work. Well, let's figure out what it is. We figured it out, and then we solved the problem. Okay. Okay, so according to Einstein, if we treat this one with relativity now, this one's got Kayla both places. How fast would that pitch be now? So we want to find the velocity of the ball relative to Zach. We'd have to use the two other component speeds to do that. The velocity of the truck relative to Zach, and the velocity of the truck relative to the ball. Here, we're actually going to have to use the real value of C, 3.0 times 10 to the 8 squared. So we'd have the truck to Zach is 22 meters per second, plus the truck to the ball, which is 27 meters per second, over 1 plus their product, divided by the speed of light, which is our 3.0 times 10 to the 8 meters per second, and square that. Yep.
You want me to tell you what I got?
Can I guess?
Sure.
49?
Uh-huh.
Yep. Exactly the same as we would have gotten otherwise, because this term is so small, your calculator can't even keep track of it. That's pretty good too. 48.999, a whole bunch of nines, right?
So
How many
slower.
nines?
Just 4.
Okay. only 4 nines. That's not too bad. Way below the number of significant digits we have. Nine, 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 nine. What else did you have in there?
0298.
So certainly to our 2 significant digits that we've got, 49 meters per second, but ever so much smaller because of that factor of relativity. Not really measurable, at least not by Zach as he tries to dodge the truck and the ball. Well, of course she's throwing it at you. She's probably laughing madly as she's doing it.
That sounds like
She'll do it too. She's crazy.
this is Kayla. This is Kayla.
This is no. This is hypothetical, Kayla and Zach.
Really? It sounds a lot like real
Might be
Kayla.
real Kayla.
Yes, Elsa.
I'm confused when you use like just the adding the numbers and
It really depends. Very good question, and I want to hit this again. It really depends on the speeds. So let me bring that up again. I showed this the other day, but it's worthwhile looking at again. The different speeds and how much of an effect any of these things have, or the speed has on any of our normal physics. So this is showing, I should say, the relative speed. So I should add that. Let me add that to it. Axis titles. This is the speed in terms of light. This is 1 over the radical, so our normal term there. 1 over the square root of v squared plus c squared. What this is showing is how much of an effect traveling at the high speed gives us. So if this is still low, we don't have to worry about it at all. Up to about 0.2 times c, there's almost no effect that we would normally measure. As we go up to about 0.5, now there gets to be a little bit of an effect, but not until after 0.5 c does it really become noticeable. So basically, at least in this class, whenever the times you need to worry about this is when the speed includes something relating it to the speed of light, like c. If it's point something times c, use all of these things. If it's not, you probably can ignore it. Use your judgment, so kind of compare it to it, because there could be it, like on the final, hint, hint, there could be something like, oh, this thing's traveling at 2 times 10 to the 8 meters per second. How far could it go to an outside observer in this amount of time? That's a big enough speed that you're going to, oh, that's getting kind of close to the speed of light. Better use relativity. But if it's anything under 1,000 or 10,000 meters per second, you don't have to worry about it at all. It's not a significant effect.
So if you're on a ship that's going like 0.9999, however many nines, close to the speed of light,
Yep.
and you walk forward, would that just add like an immeasurable amount, like another?
Yeah,
time?
because then your second time here, if you've already got 0.999 whatever c, and you're adding 0.0000 c, and keep going adding the zeros, that's not going to make much of a difference up here. These two are going to multiply out to be something relatively small. Since this one's big, but that one's really small, it'll be a lot smaller than this, so you won't see very much of an effect on it. Yes, Elsa.
So in this case of the pitch, could we just add it?
You would just add it normally.
Just because it's
And that's what we, and that's why what we saw really. Did you do, in your first physics, did you do anything with something called significant digits? How many numbers you should report in an answer? We do a lot of that. but I'll try and be kind as you're learning and picking it up. When you've got things that are going into the calculation with only 2 digits here, you're really only allowed 2 digits in your answer. This, and Zach knew that, but this would not be an acceptable answer with 22 and 27 meters per second as your measurement, because there's too much added information here.
So in the test, I would just write 49.
Yeah, you just write 49. And I'll try and work with you a little before then to get at least somewhat comfortable with it. It's very easy to get off by 1 decimal place, but we'll never have things that we just stretch out unless I give you that many numbers to start with. We're going to round it a lot. We don't really have time to go into the next thing, but I want to give you a teaser.
The whole shebang.
The whole shebang. Because now this is all of the stuff that we're going to be learning and practicing on special relativity, all rolled into one. So no new stuff at this point. We've got a week and a half. Where are we? We've got a week and a half now to practice and solidify all this stuff. We'll cover a little bit extra, how is this applied, that sort of stuff. But from here on out, it's practice and master this weird stuff. So we'll be looking at a deep space probe traveling at 0.97 c relative to an observer, launches a baseball alarm clock at a speed of negative 0.6 c, so opposite direction relative to itself. How fast are all these? How fast would it move to an outside observer? What time would it report to an outside observer? What would its mass be? All of those things.
Tomorrow or